Thank you. And this is joint work with Christian Wolf-Nielsen. Okay, so the idea of spanners is that sometimes we don't really need the entire graph. For some algorithmic purposes, we might be willing to settle for a sparse graph that approximately preserves the distances in the original graph. And spanners are used in many distributed applications. Here are some examples. Okay, so let's consider this example. And assume we want to find a spanner for this example. We want to find some sparse subgraph that approximately preserves the distances in this graph. So if you took the following blue subgraph, you can see that every two nodes that are connected by an edge in the original graph now have a path of at most 2 blue edges. Okay, so the distances in this blue subgraph is at most twice the distances in the original graph. Okay, and in this case, we say that the stretch of the spanner is 2. So the formal definition of multiplicative spanners is the following. So we say that a subgraph H is a K-spanner or a spanner with K-stretch if for every 2 vertices S and T, the distance between S and T in the subgraph H is at most K times their distance in G. Okay, and a very well-known theorem on spanners is that one can efficiently construct a 2K minus 1 spanner, a spanner with 2K minus 1 stretch, with this number of edges, n to the 1 plus 1 over K. And based on Geer's conjecture by Erdős, this trade-off is also conjectured to be tight. Okay, so if you believe the Geer's conjecture, you get a lower bound of with this trade-off. Okay, so here I also said lower bound. So how do we get this algorithm? How do we get this result? So there is a very simple greedy algorithm that achieves this bound. For parameter k, we want 2k minus 1 stretch. So if we just do the following, we just get this trade-off of 2k minus 1 stretch and n to the 1 plus 1 over k number of edges. So we simply take all the edges in the graph, order them, sort them in some increasing order or non-decreasing order, and then we examine one by one. And for each edge uv that we examine, we take the edge uv to the spanner if the current distance in the constructed spanner between u and v is bigger than 2k minus 1, the weight of the edge. Okay, so I hope it should be not hard to see that we already get, by construction, we get a 2k minus 1 stretch. Okay, because for every edge, we either have an alternative path of length 2k minus 1 to it, or we take the edge. Okay, and I'm not going to show it, but it's not hard to see. It's not hard to show that this algorithm also produces a sparse graph. The number of edges here is at most n to the 1 plus 1 over k, and the way to show it is to show that there are no small cycles in the graph. Okay, and then there is a lemma, a cute lemma that shows that if there are no short cycle in the graph, then also there cannot be too many number of edges. Okay, so this simple algorithm already gets the conjecture optimal bounds of 2k minus 1 stretch and n to the 1 plus 1 over k number of edges. Okay, so counting the number of edges is one measure for the sparseness of the graph. We can also think on other measures, and one very natural measure is the weight of the spanner, the total sum of the weights of all edges in our spanner. Okay, so in this talk, we will focus on the weight of the spanner, and we will try to minimize that. So what can we hope for with respect to the weight of the spanner? So clearly, if we just want connectivity, we need to pay at least the MST. So we cannot hope to get something better than the weight of the MST. And actually, if we believe the Geer's conjecture, then we can also get similar lower bound. saying that we cannot hope for better than paying n to the 1 over k. If we want 2k minus 1 stretch, we cannot hope to get better than n to the 1 over k times the weight of the spanner. Okay, so that's the best trade-off, 2k minus 1 stretch and this weight that we can hope for. And with the lightness of H is defined as the ratio between the weight of our spanner and the MST. Okay, so the best lightness we can hope for with 2k minus 1 stretch is n to the 1 over k. Okay, so let me mention some related work on this problem. So I'll mention here only the works on general graphs. So this problem was also studied a lot actually for other special families of graphs, such as geometric, Euclidean, and bounded doubling dimension. Okay, so here I'm only going to mention the works for general graphs. Okay, so in 63, it was shown that if you just use the greedy spanner that we saw with 2k minus 1 stretch, then this is the lightness that you get. Maybe better, but they show about that this is at most the lightness that you get. Later, it was shown that actually, if you're willing to pay a bit more in the stretch, not 2k minus 1, but another factor of 1 plus epsilon in the stretch, then the greedy spanner itself already gives you a much better lightness of k times n to the 1 over k. Okay, so a natural question is, can we remove this k? Or do we need it? So recently, this gang showed that you can actually, it's not essential having this factor of k here, and you can get something slightly better. You can get the greedy spanner itself with a much more involved analysis already gives a lightness of k over log k. Okay, and in this work, we shave this k completely, and we show that we show a different construction. It's not a greedy spanner anymore, and we show that you can get 2 plus epsilon k stretch with this number of edges and with lightness of n to the 1 over k. Okay, so if you believe the Gibbs conjecture, it's optimal up to the 1 plus epsilon factor here in the stretch. And for the rest of the talk, for simplicity, I will show a much simpler construction that does not remove the k completely, but get a low k factor here. Okay, and we will use 2 claims that if I'll have time in the end of the talk, I'll prove them. For now, you will just need to believe me. So the first claim is that we can always reduce to the case. So, okay, so say this is our MST. And again, we want to compare ourselves against the weight of the MST. So the claim says that we can always reduce to the case where all the weights in the MST are 1. Okay, we assume that all the weights in the spanner is at least the minimal weight is 1. And without lots of generality, we can always reduce to the case where all the weights in the MST are 1. And the idea is just to round each edge here and add some dummy nodes in the middle to get this nice property. Okay, so if I have time in the end, I will show it. It's not completely difficult. Okay, so that's the first assumption that we make. The second assumption that we make is that we only need to take care of weights up to 2k. Okay, so again, if I'll have time in the end, I'll show it. But the general idea is that larger weights are actually easier. Why? So say that I have to handle much larger weights. So what can I do? I can take my MST. I can always just add the MST, assume that my MST is in my spanner. It doesn't cost much. And I can take the MST and use the MST to kind of group the nodes into some clusters, such that in each such cluster, the diameter the diameter in the MST is small. Okay, so just using the edges of the MST, I can traverse from every node in a cluster to every other node in a cluster using just a very small diameter. And then I can just consider each such cluster as a node. And if the weights of the edges are very large, then I have to go with a very large edge and get into a cluster for every pass, and then I will do some detour here, but the detour here is so small compared to the weight that I didn't lose much. Okay, so I can always, so for larger and larger weights, I can just take larger and larger clusters, and in the end we will get a geometric series. Okay, so the hard part is to handle up to 2K. So I'm slightly cheating here, because it's true that we need to handle only that larger edge weights are easier, but we also have the MST edges that are of weight 1. So, and we need to use them. So if I go into a cluster with weight 1 and I do the detour here, then actually I can get a very bad stretch. So we need to play a bit with the weights of the MST too. But that's the general idea. Okay, so the rest of the talk, or almost the rest of the talk, will assume these two assumptions, that the edges of the MST are all 1, and that all the weights in our graph is at most 2K. Okay. Okay, so and a simple claim that we will use is the following. So let's consider our MST, again, all weights 1, with all weights 1. We can always partition the nodes. So we get a parameter R. We can also partition the nodes in the MST into clusters with diameter R, diameter in M, this number of clusters. So we can always have n, roughly n to n over R clusters of diameter in M R. So why we can do that? So let's assume it's easier to assume that the MST is just a pass, even though it's not necessarily the case. So if the MST is just a pass, it's very easy to do. We can just take the first R edges, cluster them together, and then take the next R edges and cluster them together. Okay, so we will get that way that the diameter in each such cluster is R, and we have n over R clusters. So, and actually, if the MST is not a pass, if it's denser, that it's actually just more convenient for us. Okay, so actually, the worst case is it is when it is a pass. Okay, you can also get the same claim, even if it's not a pass. But for simplicity, let's think that the MST is a pass. Okay, so let's, as a first step, see how we get lightness of k times n to the 1 over k. And later we will see how to improve this k to low k. Okay, so again, we assume that the weights here are all 1 and that we need to handle weights up to 2k. So we will have just k buckets. In each bucket, we will handle weights 2 to the i to 2 to the i plus 1. Okay, so we have k buckets. And we will show now how to handle the bucket I, and how much we need to pay, how much, the weight that we need to pay for the edges that we take for our spanner to handle edges in this bucket. So by saying handling or satisfying edges in this bucket, so for every edge, what we need to show is that we either take this edge to the spanner, or we have a short alternative path to this edge. Okay, so if we have this property for every edge, we will get a spanner. Okay, so now we are only looking on edges in this bucket, between 2 to the I and 2 to the I plus 1. So basically what we can do is we can use the previous claim and just cluster, take the MST, and cluster the nodes in the MST into clusters of roughly this diameter. Epsilon times 2 to the I. Okay, so we will have roughly n over this number of clusters. And let's ignore epsilon factor, so we have roughly n over 2 to the I number of clusters, each with this diameter. And now what we can do, we can just take each such diameter and contract it. Consider it, think of it as one node. And so we have this node, and now we have we add to this contracted graph all the edges of weight between in this bucket. And we ignore now the edges of the MST between the clusters. Okay, so we have all the clusters here of this diameter and the red edges in this bucket. And now what we do, we simply invoke our greedy spanner on this contracted graph. Okay, so what do we get? So let's see that the stretch is fine. So why the stretch is fine? So the greedy spanner promised me that for every edge that I did, every edge, red edge, I either took it, and if I took it, great. And if I didn't take it, then it means that I have some other path of length 2k, roughly 2k, of edges that I did took to the spanner. That the sum of the weights of these edges is at most 2k minus 1, the weight of this edge. And so the weight of each edge here is in this bucket, but I also, in order really to get a path in my spanner, I also have, when I enter a cluster, I also might need to do some small detour here in order to take the next edge. But the detour here, we made sure that it will be very small compared to the entering edge. So the edge here is 2i, and the detour that I need to do is only epsilon 2 to the I. Okay, so the detours, all the detours do not add much to the total length of the path between these endpoints. Okay, so overall, I guess that I get a good stretch with this additional 1 plus epsilon factor to my spanner. Okay, so we only need to show now how much weight did we pay for this level. Okay, so how many, let's see, the number of nodes, the number of the nodes that I have in the graph that I constructed here is the number of clusters. That's the way we constructed it, which is this number roughly n over 2 to the I. And the greedy spanner guarantees me that it will return me a spanner with this number of edges. Each edge here is of weight 2 to the I, so I need to multiply it by 2 to the I, and these two terms cancel one another. And we get that the weight of the greedy spanner for this level is n to the 1 plus 1 over k. And we have k levels, so for all levels, we can get this weight. So this lightness is k times n to the 1 over k, because the MST is n. Any questions? Okay. Okay, so now we want to improve that, the k factor into a log k factor. So previously what we did is the way we constructed the clusters, we kind of constructed them independently. For each level I, we constructed different clusters. We didn't really care about how they relate to one another. But we can simply also do it in a bit more hierarchical way, such that, say that this is our initial clusters for the first level. Then in the second level, I can take clusters such that each cluster is just the union, this joint union of some clusters from previous level. Okay, so if again our MST is a line, and this is the first clusters. The second cluster, we can just simply take, say, 2 adjacent clusters and make them together one cluster. Okay, and we can continue this way hierarchically. Okay, so now each cluster here is just a union of some clusters from previous level, and each previous level clusters belong to only one cluster in the next level. Okay. Let's assume now, for simplicity, that the first diameter of cluster that I have is k. Okay, I hope that it will be clear in a second why. Okay, so let's assume this cluster are all of diameter roughly k. And let's consider now, let's try to satisfy only edges of weight 1. Okay, so actually satisfying edges of weight 1 is easy, but we will do it, of course, for every level later. Okay, so now I'm trying to satisfy only edges of weight 1, and I want to use the clusters here for this purpose. So if I got lucky, and every cluster here has, so now I'm looking at all edges between clusters in this level, and I remove multiple edges. Okay, so I don't have multiple edges. I just pick one of them. So if I got lucky, and the number of edges incident to each cluster is constant, and this happens for every level. So in this level, I will look on edges of weight 1, here edge of weight 2, 4, and so on. So if this happens in all levels, then I'm actually done. So why? So let's see how much I pay, how much weight I pay in this level. So I have roughly n over k clusters here, right? And the weight, and for each cluster, I assume that I have only constant number of incident edges of weight 1. So for each cluster, I actually pay only O of 1 weight. So overall, for all clusters, I pay n over k weight. And we can do that similarly for every level. And since we have only k levels, then overall, we will pay only O of n weight. Okay. So if I got lucky and the number of incident edges is always constant for every level, then we are done. Okay, but what do we do now with edges with high degree clusters? Okay, so if this cluster has many incident edges of weight 1, then we couldn't do this trick. Okay, so what do we do with high degree clusters? So let's go back to the properties that we need actually from this cluster. So what property do we need? We need a property that we don't have too many clusters in every level. Right? For this level, we wanted only, if the diameter is r, we wanted to have only n over r number of clusters. And the second property that we need is the diameter. Okay, so this is the two properties that we played off, the trade-off between the diameter and the number of clusters. But now, if you give me a cluster that has many incident edges touching it, then I can actually use it. So I don't care the number of nodes in each cluster. I only care about the diameter. If you manage to give me a cluster with many more nodes, but with the same diameter, then it's actually great. I can treat most of these nodes as if they disappeared. So that's what I'll do here. If I have high degree clusters, I will use all these incident edges. I will now construct these clusters a bit differently by exploiting these high degree clusters, such that I will take this cluster with all of these incident edges, and I will make it a cluster, again, all with small diameter, but with many more nodes. Okay, so before that, say I could only take 2 clusters and merge them together to get a cluster of roughly 2k. Now I can take, depending on my parameter, I can take 10 of them. Okay, so more than half of them disappeared. So now I will use the clusters that disappeared to do something else. So what else can I do? So I know that all the low degree clusters here are already covered. And for the high degree, I know that at least half of them will disappear in the next level. So what I will do is I will take, say that we are now handling this level. We take all the high degree clusters here. And again, we change the way we constructed the clusters. We use, if this is a heavy cluster, we take all its incident clusters and merge them into one small diameter cluster. So now we have less clusters here. And I will take all the clusters. So one attempt to do it is to take all the clusters here now, the heavy clusters, put them aside, construct a new graph with this with these heavy clusters and take all the edges incident to them, that both endpoints are heavy clusters. And now I can just construct a greedy spanner on this cluster. Okay, so half of the nodes here will disappear. So amortizing, every node appears in only one spanner. So I won't pay too much. So on every node, on average, I want to get n to the 1 plus 1 over k weight. So for every node, or times log k. So for every node, I can pay roughly n to the 1 over k. So if I construct a spanner here, and on average, every node, I pay the number of nodes here times n to the 1 over k, then I'm done. So, okay. Okay, so doing that like that, we won't get a good stretch though, right? Because the diameter here is k, and the edges that we are looking are of weight 1, right? We always have this gap. So if I'll construct a spanner, a greedy spanner on this graph, I will get a terrible stretch of k squared. Okay, every incident edge of weight 1 to the cluster, I might need to do a detour here of weight k. Okay, so I don't want to do that. But what I can do instead is, so let's say that now we are looking on level I. So instead of looking on all high degree clusters on level I and put them aside, I will look on all high degree clusters of level I. I will go log k, or a bit more than log k, level back. For each such cluster, I know it's a union of some clusters of level I minus log k here. And I will take these small clusters that are contained in these big, heavy clusters, and I will put them aside. Okay? And now I will construct a spanner on these clusters. Okay, so I will go roughly log k levels, such that if I want to satisfy edges of weight 2 to the I will go enough level back so the diameter is epsilon 2 to the I. Okay, and now I will construct a greedy spanner on this graph. So now the stretch is fine, because every edge of 2 to the I just do a small detour of epsilon 2 to the I here, so I don't pay much. So now the stretch is fine, and the weight is also fine, because, again, we saw it before, the 2 to the I here and the 2 to the I here cancel each other. Okay, so every node inside this cluster appears in only one spanner, or half of the nodes here pays for the other half. So on average, every node appears on only two spanners. And the weight of this total spanner will be the number of nodes here times n to the 1 over k. Again, because these two factors, as we saw before, cancel one another. Okay, any questions? That's a construction with the low k factor. So why do we get low k? So we had to go before, if we just construct the greedy spanner on this level, then we didn't get a good stretch, but we know that on the next level, half of the nodes here will disappear. But now this is not the case anymore, right? Because we go log k level back. So it will take these nodes here to disappear only, they will disappear, half of them will disappear only log k, after log k levels. So for each node here, for each cluster here, we can look on the first time it contains in a heavy cluster. Okay, so say these nodes, for these nodes, these are the first level, they are contained in a heavy cluster. So we know for all levels below, they did not appear in any heavy cluster or in any spanner. So this is the first time I actually add the nodes in these clusters to a spanner. And I know that after log k levels, they will disappear. So they have only, half of them have only log k levels chance to appear in a spanner. And after log k levels, I know that half of them will disappear. Okay, so that's the general idea with getting the log k times n to the 1 over k. So any questions on the construction? Okay. And to get rid of the log k, we need to do something a bit differently. We need to look on all this log k together and do something a bit more complicated instead of doing that for every level separately. Okay, so I see that I have enough time. I will just show the two claims that I used in the construction. So the first claim that we used is that that we can always reduce to the case without changing much the number of nodes and the weights. We can always reduce to the case where the weight of the MST are all 1. Okay, so let's say this is the weight of the MST. And let's define W prime to be the average weight in the MST. So that's just the sum of the weight in the MST divided by n minus 1. Okay, so now we can look on every edge and round it up. So first of all edges in the spanner of this weight we can easily handle. So why we can easily handle all edges of that weight? We can simply take all edges of this weight and construct a greedy spanner on them. Okay, that won't cost much. It will cost n times n 1 plus 1 over k times the weight here, which we are willing to pay. Okay, so say that we don't have edges, that all our edges are of weight larger than that. We already satisfied all of the edges of weight less than that. So now what we can do is to take every edge in G and just round its weight to the nearest multiply of W prime. So that won't change the weights by much. But why? Because now we assume that all our weights are very big. So I just add W prime for every edge, so it didn't change much. So now every edge is a multiply, the weight of every edge is just a multiply of W prime. And now what I will do, okay, so that was, say, let's look on an edge in the MST. So before it was 2 W prime plus 1. Now I round it up to 3 W prime. And the next step, what I will do, just for the edges of the MST, I will take each such edge of the MST, and I will add some dummy nodes here to make every edge of weight W prime. So if the weight here is 3 W prime, I will add 2 dummy nodes, and the weight of each edge now is W prime. And you can see that I did not add too many number of nodes here. So by rounding up every edge in the MST to the nearest W prime, I could only double the weight of the MST. So adding these dummy nodes, we can show that you only added maybe n number of nodes more. Okay, so we didn't change much the weights, and we didn't add too many nodes. And now we have that the MST are all of uniform weight. Now we can just divide everything by W prime, and it won't change anything. Okay, so now we reduce to the case where the weight of each edge in the MST is 1. Okay, and the next claim that we used is that we only need to take care of weights of 2k, 2 to the k. So I said before what we can do with larger weight. Let's see it slightly more formally. So let's say that now I want to handle edge weights between 2k to 2k plus 1. Okay, and in general I will do it to every 2 to the ik to the 2 to the ik plus 1. So now what we can do is we can use the previous claim of clustering and cluster. We can partition the tree. Now our tree is again of weight 1 because we reduced to this case. We can partition the tree into this number of clusters with this diameter. And now, so I have now less, and each cluster I just contract to one node, so I have less nodes now. And the diameter of each cluster is small compared to the weights that I'm trying to cover now. But actually now we also have the weights of the MST of weight 1, so I cannot just like add them into the constructed graph like that, because then I can use a weight 1 and do a huge detour here, and I will get a terrible stretch. So what we do is we just take all the MST edge weights and increase them to 2K. Okay, so let's see what's the weight of the new MST. So the weight of the new MST is the number of nodes times 2K, which is again roughly O of n. Okay, so we didn't change much the weight of the MST. It stays almost the same. Actually, we a bit increase it to be n over epsilon. But let's ignore epsilon factor. So we didn't change much the weight of the MST, but we changed the number of nodes. And previously what we pay is the number of nodes to 1 over k times the weight of the MST. So that didn't change much, but that changed. And we can show that if we just sum over all buckets of 2 to the ik to 2 to the ik plus 1, then this sum is just a geometric series. Okay, so just to summarize, we got what we showed here is low k times n to the 1 over k lightness. In the paper, we showed n to the 1 over k lightness with this number of edges and this stretch. And we have here a dependency on epsilon. Okay? In the number of edges, we don't have a dependency on epsilon. The question that remains left is can we improve the stretch to 2k minus 1? Remove the 1 plus epsilon additional factor and stretch that we get. Any questions? Thank you.
So in particular for stretch log n, you get constant times the MST, is that right?
Yeah.
And the previously it was just log n, right? Log n times
Yes.
MST.
Yeah.
So about the construction time, instead of the greedy spanner, could you use any spanner construction that keeps the trade-off?
Yeah.
So and this dominates the running time, basically.
That dominates running time, yeah. But for other spanner, I mean, that's what we know, like efficient construction for spanners, we know how to do only for the greedy spanners. So, like if you don't want the factor K.
I see.
Other more efficient construction of spanners, they have the factor K. So if you use them.
Yeah.
So for stretch 2k minus 1, you showed that the best lightness was NLK? Oh.
The stretch was a bit more. We had 2k minus 1 times 1 plus epsilon.
Lightness log k. Times, yeah, okay. But then the...
Yeah, you can plug it.
The first slide you showed that for 2k minus 1
Ah.
was n over k.
On over k, yeah.
And is that the only thing known for 2k minus 1?
Now you can plug different parameters here to get 2k minus 1.
Okay.
And you will get a better lightness than n over k.
What's the best known for without the 1 plus epsilon? Yeah.
We just need to calculate it. Do that equal to k minus 1. That will give the best bounds. You will get a dependency here, exponentially in epsilon.